I want to show you one more property of chaotic systems that really explains this, among other things, the sensitive dependence on initial conditions, and explains why a system can exhibit something like that. So I want to consider a simple mathematical example, but it's also a physical example, and you can do this. This particular function that I'm going to show you is called the Baker's transformation. And it goes like this. I want you to consider a square which you may think of as a square of dough. And right now, it has unit dimensions. And then just so that we can follow things, we're going to put a little smiley face into the dough. So this is the initial condition. Now, we're going to take that, and this is a discrete time system. Our first act is going to be to take a rolling pin on top of this and roll it down so that it is half the height and twice the width. And then Mr. Happy is going to look like this. Okay. Now, the next step we're going to do is we're going to cut this in half and take this portion and fold it up on top of this one like that. So now let me see if I can draw that. Here is the left-hand side, and it's going to be half of the face, one left eye, and half of the mouth. And then the other half is going to go up on top, and it's going to look like the other half of the face, but as you see, the eye is now on the bottom, and the other half of the mouth is up like that because we folded it up this way. So this to this to this, that's not drawn very well, but this was twice as wide and half as high, and when we took that back, we now once again have the unit square. But it's more complicated. Now I want to put that back here and repeat that process. Roll it to half height, fold it over, put it back. Roll it to half height, fold it over, put it back. Repeat that cycle many times, let's say 50 times. I won't attempt to draw the second stage. You see what would happen. This would now be twice the width. This two-part object is now going to be twice the width and half the height. Then we're going to cut it in half and fold it over. We're now going to have 4 segments of faces. And that's going to be back in the unit square. And as a matter of fact, the number of layers is going to go as 2 to the n, where n is the number of times we do the iteration. So now if you imagine n getting large, you see that the Baker's transformation is going to yield a very, very complex object. Mr. Happy has now been broken up into trillions of little pieces by a completely deterministic process. And this stretch, fold, reinsert, stretch, fold, reinsert is the mechanism that is producing this complexity. Now ask yourself the following question. Let's take 2 raisins in the dough. And they could be those 2, for example, very close to begin with. Now we roll it down, and these 2 are further apart. I'm exaggerating, but these 2 are further apart. In fact, they're twice as far apart as they were here. But they're still on the left-hand side, and then that gets folded over, and now the 2 are here and here. Now let's stretch it double again, and you see that pretty soon this raisin is going to be in the right-hand side of the object because I keep stretching it. Sooner or later, this raisin is going to get to the right-hand side. The minute the raisin gets to the right-hand side, it now gets sent up here. So now the 2 raisins are in different parts. You repeat that, you repeat that, you repeat that. And now, after, let's say, 50 cycles of this stretch, fold, reinsert, I tell you that raisin number 1 is in the upper half of the box. And I ask you, place your bets on where raisin number 2 is. Given that raisin number 1 is in the upper half, and the answer is even money. Cannot predict with any knowledge at all whether that second raisin is going to be in the same half box as the first one. So, this is obviously sensitive dependence on initial conditions. 2 correlated raisins quickly become completely uncorrelated. What is causing the sensitive dependence on initial conditions is the stretching that is being carried out by this function that is spreading those 2 points apart, and then the folding, which is effectively sending it back into the same general region. But as this process is iterated, those 2 are going to become completely independent of each other. And so stretching, folding, and reinsertion is a mechanism for producing chaos and explicitly for generating sensitive dependence on initial conditions. So this process, roll it flat, fold it over, reinsert it, roll it flat, fold it over, reinsert it, is actually a practical device for producing chaos. It was discovered, interestingly, by Japanese sword makers 1,000 years ago. I think it was 1100 or something like that. In making a sword, the best swords are combinations of 2 metals. You want hardness and sharpness or whatever. And so you start off with 2 different metals. We'll call them 1 and 2. And this is metal number 1, and this is metal number 2. Now what you want to do is produce a complete mixture of these 2 elements. And how are you going to do that? Well, you might say, okay, melt them both down, pour them together, mix it up, let it cool. Not good. Melting the metal destroys the hardness. So melting is not an option. So how are we going to mix 2 metals without melting them? So the sword makers came up with a clever idea. they just took the two sheets of metal, they laid one on top of another, and then they rolled it to twice the width and half the height. And then they took this section and folded it back up on top of that. And then they rolled it out again, and they did it again, and they rolled it out again and did it again. And if you can do that 50 times, you get 2 to the 50th little layers here of 1s and 2s and 1s and 2s. And the resulting object is a mixture, a cold mixture of the two metals, 1 and 2, produced by this mixing process. So I want to show you this Baker's transformation, this stretch, fold, reinsert, as the cause of chaos in that discrete time logistic function. So let's remind ourselves what it is. We have xn plus 1 as a function of xn. And in the chaotic regime, it's going to look like that. And let's draw in our little reference line. And I want to look at a little interval. Let's get a better marker for that interval. Here's a little interval on the x-axis. And I want to ask, what is going to happen to the points on that interval? Well, they're all going to go up to the function, and they're going to get sent over here. And now I want you to notice something. This distance is greater than this distance. And the reason why the difference between f of this point and f of this point is greater than this point minus this point, the reason why this interval is bigger than this interval, is because the slope of the function is steeper than 1. Here's the 1, 1 line. If the function had just been the 1, 1 line, then this interval would have been mapped to an identical interval over here. But the slope of the function is steeper than 1, and so this interval is going to get stretched by the function whose slope is steeper than 1. That follows automatically. Those are two ways of saying the same thing. So our first act is a stretching of this interval. Now let's ask what happens. Well, as you know, we have to get that interval back down onto the x-axis, which we do. It now looks like this, and this equals this. And now we need to shoot this interval up to the function to get the second iterate. But when we do that, we see something very interesting, which is that this interval is going to get folded over. As it gets mapped back onto here, this part of the function is going to get mapped to here. It's now going to get mapped to a shorter interval that has been mapped 2 to 1. This point and this point are both going to get mapped to that point. So this interval has been folded over and mapped back onto here. And then we take that interval over here and we take it down to here and we shoot it up to the function and we get another interval. So you see that in the discrete logistic function, there is a stretching and folding and reinsertion. And that is the, if you wish, the mechanism of chaos in the discrete logistic function. We can also see exactly the same sequence. I mean, qualitatively, stretching, folding, reinsertion in a continuous differential equation in the food chain attractor. So we simulated the food chain attractor, and beauty of computers, we took 10,000 initial conditions for that differential equation, separated by 1 part in 10 million. So the 10,000 initial conditions make a tiny, tiny little green dot in the handle of the attractor. Those are our initial conditions. Now we're going to evolve the system forward. The system has a period of about 100. And you see that by 300, that tiny little dot has elongated into a macroscopically visible string. So it has elongated, it has been stretched. Then the next couple of times around, it stretches even further, and then the long filament, that is the result of the initial condition, then gets in a situation where it gets transformed back into the body, folded over. So now that filament is folded over. Now we shoot it around it again, and the folding over gets folded over. And after 50 iterations around the attractor, you see that the stretching, folding, reinsertion, stretching, folding, reinsertion has fragmented the filament into a dust that is distributed over the whole attractor. So there again is a randomization, except I should say pseudo-randomization, of the initial condition produced by stretching, folding, and reinsertion in the food chain attractor.